Okay, so the toolkit function that I'm going to be using most in this discussion is going to be the absolute value of x. And the nice part about this function is that it has a nice sharp point at 0, 0. And we can see what happens when we move this graph around by where that little vertex goes. And so we don't have to calculate very many values to see what happens when we start changing around the absolute value of x. But for now, this is the basic function I'm going to be using. Okay, so let's say we have this function where I'm going to add 2 to my toolkit function f at x. So I'm going to evaluate these things at my 3 points, the -1, 0, and 1. And so f at x equals 1, 0, and 1, but g at x is going to be 2 more than that. And you can see what happens when I add 2 to the absolute value of x. It just moves the whole graph up by 2. All right, so this is the simplest translation you can make, that you take any graph, you add a constant to it, and it moves that graph either up if it's positive or it moves it down if it's negative. And so we have a generalization here. So if we say, if g at x equals f at x plus k, k moves the graph either up or down k units. Okay, so think about some other toolkit functions, like if you have x squared. If you have x squared plus 2, it moves the whole parabola up. X squared minus 2, it moves the whole parabola down. Same thing with the square root of x. It moves the whole thing up. If it's the square root of x plus 2, square root of x minus 2. Okay, so now let's not add 2 to the function. Let's put 2 inside of the function and say we're going to start using f at x minus 2. And so what I have here is that if I just use the first 3 values, the -1, the 0, and the 1, my g at x is going to be 3, 2, 1. Now, I'm on a downward slope, and I know that I'm supposed to look like this this kind of V-shaped graph, and so I'm adding on 2 more points, x equals 2 and x equals 3, to see what really happens. All right, so I can evaluate f at x, and I get my list of numbers, 1, 0, 1, 2, 3. G at x is going to be, if I take -1 minus 2, that's -3, so positive value of 3 is 3, -3 is 3. Same thing with f at 0 minus 2 will give me, not f, g. G at 0 minus 2 is 2. G at 1 is going to be 1. G at 2 is 0. G at 3 is 1. So my whole graph moves to the right by 2 units. So here's my generalization. So if I take some value h, it moves it to the right by h units. Now note the negative sign here. It moves opposite of where you would expect, that x increases as you move to the right, but when you say x minus h, if h is positive, then it's going to move it to the right. If h is negative, it's going to look like something like h plus or x plus 2, right? That's going to move it to the left if I do x plus 2. So this is one of those that just be cognizant of the sign. We're looking at a negative sign. When h is positive, it moves it right. When h is negative, then it moves it left. Okay, so I'm going to switch toolkit functions just to give me a little something different to look at. What do you expect here? So if f at x equals x squared, let's say g at x equals x minus 2 squared plus 3. So I have both things going on. That first one, I'm adding 3 to the function. On the inside of the function, if you want to look at it that way, I'm subtracting 2. So what happens here? Yes?
The problem moves up 3 and then it moves to the right 2.
Moves up 3, right 2. So every point is 2 units right and 3 units up. And so if this is what my original graph looks like, what's at the top, the new graph, I graphed it wrong because I went up 2 and right 3. That should be, let me change this. So my vertex is going to be up 3 and over 2. So it's actually going to be here like that. All right, everybody follow? I'm going to stop here.